Hello! Welcome back. It is more series, section 11.2. We'll probably have one other short lecture on this section, but this is another big topic in this section, so let's just dive right in. Okay, so here we go. Today our topic in section 11.2 is a type of series that seems to come up in surprisingly many scenarios in physical and mathematical and physics applications. In all kinds of different contexts. So that type of series is called a geometric series. A geometric series. So that's mainly what we're going to talk about today. So what is a geometric series, right? We're really good with understanding what series are now. We know when we see this word, we should think what symbol? Good, right? Series is a sum of infinitely many numbers, right? And so we have our summation, like an S, okay? Summation notation, and we sum something up. We call them A sub n usually. But what does a geometric series look like? Well, I'm going to kind of go with your book's notation. So R is pretty classic, and your book does R to the n minus 1, where we start counting at n equals 1 and go on to infinity, okay? Which means we just keep going, adding forever, right? So let's write down what this means, okay? So if n is 1, then R to the 1 minus 1 is R to the 0, which is, good, 1, right? Then what are we going to do? Add. Right? That's what sum means. Then we're going to increment our counter, right, by 1. So then we get R to the 2 minus 1, which is just R to the 1, right? Then we add. Then we get what? Increment the counter. So it'll be 3 for our third term, right? This will be our third term. And what do we get? R to the 3 minus 1, which is R squared. Do you see the pattern here? Plus, what will the next guy be? Good. R cubed plus R to the 4th. On and on forever. Yeah? Okay. What is R? R is some fixed real number. Okay? So R is some fixed real number, right? R is a constant. And in general, we're not thinking about R being 0. Okay? Because if we were, technically, it's a little bit weird if things are 0, but if you're thinking about 0 raised to a power, then you're just talking about 0 plus 0 plus 0 plus 0 plus 0, which is 0. Okay? Now, this is the book's notation. Your book also uses the sum n equals 1 to infinity of a times r to the n minus 1. Okay? So we'll just put that over here to the side. So this is the case where a is what? Good. A is 1, right? And so for us, this a is not necessary here. We're going to have a way of dealing with this guy. This is just some other constant. So for what we'll do, what we'll develop, whoops, didn't give myself enough space. What we'll develop, we'll just take a to be 1, and then we'll have a theorem about constant multiples, and we won't have to worry about that guy A, okay? But your book will keep that guy in there. What's another thing? So then all this would just be multiplied by A, right? A plus AR, okay? I just want to avoid that. This is a lot simpler, yeah? Okay. So what else is another way to write this exact same series? This guy is also known as another way of writing it, which I actually prefer, where we can just do R to the n, okay? And so if we're summing R to the n, then where should our counter n start? You guys tell me, what do you think? If we want that to be the exact same sum as that, right? We want to keep going forever, but the question is, where should the counter start, right? If I want that to be 1 plus R squared, right? Plus R cubed, right? On and on forever. Where should I start my n? n should be 0, yeah? Okay? And so either one of these expressions is a geometric series, yeah? Your basic geometric series in its most standard form, right? Which it can also be multiplied by a constant a, okay? All right, so I prefer this one, but this is the one your book works with, so I'm going to try to stick working with that just so that you don't have as many different things to deal with. Okay, so now that we know what this geometric series thing looks like, let's see what we're going to work with. So let's look at an example, right? So we've already kind of, I'm going to erase this now because I don't need that there anymore. So for example, let's write down some specific geometric series, okay? So we have already thought about a series that looks like this. Well, actually not true. We thought about a sequence that had a similar term as the generator. So what if we go with the sum n equals 1 to infinity of 3/7 to the n minus 1, right? So this r to the n minus 1, r to the n ought to make you think about that sequence that we talked about in section 11.1. You're going to see that guy come back real quick, right? So we've got this guy. Well, let's write down what that means, right? What is that? That is just when n is 1, what do we have, right? 3/7 to the 0 power, 1, right? Plus when n is 2, 3/7 plus when n is 3, right? 3/7 squared, right? Plus when n is 4, n is 1, 2, 3, n is 4. What do we have? 3/7 cubed. And that goes on forever, right? Okay? So the question is, what does that add to? Or does it add to anything? Does it converge to something finite, or does it diverge, right? And if it does converge to something finite, can we say anything about what it does converge to? Okay? So there's one example. Let's look at another one. Okay, so call that example 1, example 2. Now we're not going to answer any of these questions yet. We're going to answer them in a little bit. So let's look at example 2. Okay, what if we do this guy, sum n equals 1 to infinity of negative 3/7 to the n minus 1. You might recognize those numbers from just things we did in 11.1, or I told you to go ahead and try to prove things about. So here we are. What is this guy? Okay, if n is 1, what do we still have, right? 1, right? It's the same thing. If n is 2, what do we have? Now 2 minus 1 is 1, so we got negative 3/7 to the 1 power, right? So are we actually going to have a plus? Nope, it's going to be a minus 3/7, right? And then when n is 3, 3 minus 1 squared, anything squared is positive, so what are we going to have? Plus a 3/7 squared. Then the next guy, when n is 4, 4 minus 1, 3, that's odd, right? A negative to an odd power is going to be negative, so it's not going to be plus. Nope, it's going to be minus 3/7 cubed, right? And it's going to continue that power, plus minus, or that pattern, plus minus, plus minus, plus minus, right? And again, the question is, does this add to anything finite? If so, what can we say? And I'm looking over here because we put a clock over here. Sorry. So I'm trying to look at you now. Just to try to keep this video from being like less than an hour, 45 minutes long, right? So does this add to anything finite, right? Or does it diverge? And if it does add to something finite, can we say what it is? Okay. So right now we really don't have a lot of, like a lot of clue about these guys. Let's look at one more. Then we're going to go explore things, and then we'll see what else we can say. We'll come back to these guys later. What about some, say, n equals 1 to infinity of, say, 2 to the n minus 1, right? Well, what would that be? It's a geometric sequence, right? You recognize this is a constant, right? Raised to either n or the n minus 1, yeah? So what is this? It's exactly that guy. So what do we have? 1 plus 2 squared, which is good. 4 plus 2 cubed, which is, yay, 8, right? Plus 2 to the 4th, which is, nice, 16. All right, do you have a sense about whether or not this series here might converge or diverge? What do you think? Does it look like that might add to something finite? That's good instinct. Good instinct. It does look like, hey, maybe that guy's diverging, right? That sum is going to grow without bound. So that is true, and we'll see that in general a little bit. But here we don't have quite so much instinct, and we're not quite sure what we're getting at. So that's what we're going to go try to study in general now. So again, look at the idea of a geometric series. The idea is there's a common ratio of R, right? So there's a common ratio of R. The next term is the previous term times R, right? The next term is the previous term times R. The next term is the previous term times R, right? Or what do I mean by a common ratio of R? If I do the next term divided by the previous term, what do I get? R, right? The next term divided by the previous term, what do I get? R, right? Does that make sense? Okay, and that would be true no matter which two pairs of terms we choose, right? Okay, no matter where. Okay, so that's the idea of the geometric series, when your series has a common ratio of successive terms of the exact same constant R. So when, and that's the thing that comes up in lots and lots and lots of different scenarios. So let's look at what we can possibly say about these series, okay? So we'll come back to these guys. It's nice you'll have them all written down in your notes. So now what I'm going to ask you is, what can, something we've already talked about, I've got to stop looking at that clock, I maybe need to move it over here. What do we have, what tools at our disposal do we have to start talking about geometric series, right, to try to figure out convergence or divergence? So what is the first thing we ought to consider and think about? I'll let you answer that while I'm erasing. So the first thing we ought to consider is or think about is what? Whoops, oh, I'm not going to get that. What does the divergence test tell us? That is pretty much the only tool, right? Does the divergence test tell us anything? That's our only quick tool that might help us, like, just kind of kick stuff out immediately, right? Divergence test only concludes divergence. All right, so let's see, right? What does the divergence test say? You should be able to write that down right now. If something, then something, right? What goes here? Okay, if the limit as n goes to infinity of the nth term that generates the series is not 0, good. If that limit isn't 0, then what can we conclude? Then the series diverges, right? Diverges is the only conclusion that can ever come out of divergence test, right? Diverges. Okay, I didn't even put the summation, where you start and where you end, because it doesn't matter, right? Okay, as far as divergence is concerned. Okay, so, and it's just shorter. Okay, that's what the divergence test says. So what is a geometric series again? Geometric series is the sum n equals 1 to infinity of r to the n minus 1. That's what we're going to look at, okay? So how do we apply the divergence test then? What is the an, right? This guy right here, right, is our a sub n, yeah? And so what should we look at? We should consider the limit as n goes goes to infinity of an, which is r to the n minus 1, right? Okay, so here's another reason why I kind of prefer the other view of geometric series, right? So if we have some n equals 1 to infinity of r to the n, then an is r to the n, and we don't have to even worry about the n minus 1. The n minus 1 isn't going to cause us an issue anyway, because why? Let's think about it. Okay, so if n is going to infinity, then where is n minus 1 going? N's growing large without bound. N minus 1 is growing large without bound, right? So this limit is equivalent to the limit, say, if we think about r to the k, just to switch letters, just to kind of, make it simpler, not to be too confusing. Basically thinking of k as n minus 1, well then where is k, n minus 1 going, right? Then if you think of that as k, where's k going? K is going to infinity, right? And this limit is equivalent to the limit as n goes to infinity of r to the n, right? All the same thing, right? The letters, okay? It just gets a little bit confusing, which would be the same thing you would be looking at if you were using this version of geometric series. Okay, so all this talking aside, then the question is, what happens to this limit, okay? Well, that limit ought to look a little familiar to you. Where did we see that limit, okay? In 11.1, we explored this limit completely. So let's recall, you might remember like a little drawing like this. We had real number line r, right? What numbers went on here that kind of changed where things happen? What happened? Good, minus 1 and 1. What did we discover for a sequence r to the n, right? We explored this in 11.1 when we looked at the sequence r to the n, right? And what did we say about that sequence? That sequence converged when r was between 0 and negative 1, when r was between negative 1 and 1, right? The sequence, r to the n, converges to 0, right? When r was equal to negative 1, right? When r was equal to negative 1, then what did we have? Negative 1 to the n. So that was just that sequence that flip-flopped back and forth, right? Negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. Did that sequence converge? No, that guy diverged, okay? And so I'm just putting the diverge ones down here. So, and then what did we also see? If r was a number between less than negative 1, right, between minus infinity and negative 1, then that sequence just bounced back and forth between negative numbers that got bigger and bigger and bigger. So it still diverged, right? What about if r was a number bigger than 1? If r was a number bigger than 1, then this was even something I suggested you try to prove for yourself, that that sequence diverged. If r was a number bigger than 1, that would go off to positive infinity, right? Right? If we had that sequence for numbers r bigger than 1, that's just like r2 to the n going off to infinity as n goes to infinity. And so the only number left was 1, and if r is 1, that sequence was just 1, 1, 1, 1, 1, 1, 1, 1, 1, right? A set, yeah? And so here we actually had that r to the n converges to 1. Now we're talking about the sequence right here. We're not talking about this series, but we need all of these limits for the sequence in order to figure this out. So what is this limit equal to? Let's see. Okay, so what do we know? We know that this limit is equal to 0, right? That limit is what that sequence would converge to. So this limit equals 0 if what is true? R is between minus 1 and 1, but not inclusive, right? Not inclusive. And then what? That limit is 1 if r equals 1, right? And that limit diverges, does not exist, right? The sequence diverges, the limit does not exist if what is true, r is less than or equal to -1, or r is greater than 1, right? R is less than or equal to -1, or r is greater than 1. Yeah? Okay. So now let's see what this buys us, okay? What does this buy us? I'm going to erase this now. Okay, so hopefully you've got that. We're trying to apply the divergence test to our geometric series, right? What does the divergence test say? If the limit isn't 0, if the limit of this term isn't 0, then I can guarantee the series diverges, right? And so, when can I guarantee the series diverges, right? 1 is not 0, doesn't exist is not 0, so therefore, for these cases, by the divergence test, the geometric series, sum r to the n, diverges whenever what is true about r, right? When r is less than or equal to -1, or r is greater than 1, or r is equal to 1, right? Diverges when r is less than or equal to -1, or r is greater than or equal to 1, right? And it's a whole lot easier to say this by just saying in one sentence, the absolute value of r is greater than or equal to 1. If the absolute value of r is greater than or equal to 1, then you're either here, r is less than or equal to -1, or you're out here, r is greater than or equal to 1. Yeah? Okay? And so there's what we know about the geometric series immediately with divergence. And so this justifies our assumption that summing 2 to the n minus 1, oh, whoops, okay, hold on, there we go, summing 2 to the n minus 1, whoops, we're getting a phone call, sorry, not going to answer that, forgot to put my home phone, we still have one of those, we're some of those dinosaurs on silent. The geometric series sum r to the n minus 1 diverges when the absolute value of r is greater than or equal to 1. Okay, so that just leaves us with what? Okay. The limit of the nth term of the geometric series is 0 when r is between -1 and 1. What does the divergence test tell us here in this case? Divergence test tells us nothing. Because the limit is 0, right? So this is the only case we now have to explore. So let's do that. While I'm erasing, now you think about this. Okay, we've utilized the divergence test, right? It's told us everything we can. Now we got to figure out what happens to the geometric series when r is between -1 and 1. What is our only remaining recourse? Very good. I think I heard someone say, oh, we have to look at the sequence of partial sums, right? We got to find Sn. Yay! Okay. All right. So let's do that. So for -1 less than r less than 1, we need to look at the sequence of partial sums What does a sequence look like? Good. A set, right? Partial sums, we use S sub n. The sequence of partial sums for the geometric series. Here's our series, sum n equals 1 to infinity of r to the n minus 1, right? Which just means 1 plus r squared plus r cubed, right? Okay, so let's get started. So what do we generally do with this? We start listing out the terms and try to come up with a closed form expression, right? And so let's see, what is S1? S1 is the first term in the series, which is just 1, right? What is S2? S2 is 1 plus r, right? What is S3? S3 is 1 plus r squared, right? The sum of the first three terms, yeah? What's S4? 1 plus r squared plus r cubed, yes? Okay, the sum of the first four terms. We're getting this. Now we want to try to look for a pattern. What do we have? Sn is 1 plus r squared, right, plus r cubed, the whole way out to what? What's going to be the final term we're adding, right? So let's compare, right? Here, this guy, what's his relation to this? 3 to 4, 2 to 3, 1 to 2, right? 0 to 1, right? This number is, good, 1 less than that number. Yeah, so what should I write there? R to the n minus 1, right? 1 less than that number. Good. So that's Sn, right? Well, this is a great, nice formula for Sn, but it's not a closed form formula. We want something closed form that only depends on n, right? And not some simple formula we can take a limit of, right? Because that's what this series means, right? What does this mean? This means, by definition, this is the sum, this is the limit as n goes to infinity of the sum, say k equals 1 to n, of r to the n minus 1, right? By definition, that's what we mean. This is just shorter to write than this, right? That's what it means by summing infinitely many things. And what is this guy? This guy is just what? What is that guy? S sub n, right? The nth partial sum. That's the definition of what it means to have a, to sum infinitely many things. Take the limit of the nth partial sum. That was the definition, right? So we need to know what is this limit. But we can't take a limit of this thing because it's not in a nice closed form. So now we have to come up with some way of getting a nice closed form, okay? So I'm just going to come over here and write down my Sn again. 1 plus r squared out to r to the n minus 1. Okay, so now here's where like the clever trick comes in. Okay, you know, sometimes you can find a pattern, but like there is no sort of pattern kind of thing that's going to help us here. We just have to do some clever algebra to come up with something that's going to kind of, you know, sort of like our telescoping sums, get rid of all the stuff in the middle. That's kind of the deal. Like, let's get rid of all the stuff in the middle and just like collapse it down to something simple. Yeah? Okay, well, what's one way to do that? Well, you know, after you've done this a long time, it seems obvious, but it wouldn't be obvious. Let's take this thing, right? Obviously stuff like the r matters. So let's multiply this guy by r, right? It seems like multiplying by r is a big thing with geometric series, right? That's the whole idea of how they're generated, each successive term. So let's multiply Sn by r, okay? So what would r times Sn be, okay? So if I multiply r times Sn, what would I get? So r times Sn, this is just a finite number of terms, so all I'm doing is distributing r times each one of these guys, right? So what I have, r, 1 times r is r, plus r squared, right? 1 times r times r is r squared, plus r times r cubed. R times r squared is r cubed, right? Plus the whole way out to what's going to be my last term? What is r times r to the n minus 1? Yeah, one more r. So I'll end with r to the n. Good. So this is r times Sn if I multiply the nth partial sum by r. Now why is this a nice thing to think about? Well, we have these two guys right here, okay? Let's subtract them. Yeah? What if I take this and I subtract that? So if I subtract on both sides, right, which is what you got to do. So if I take this thing and I subtract that, what am I going to have on the left side? Good. S sub n minus r Sn. Yeah? Now what's going to happen on the inside, right? On the right side, I've got 1 up here. I don't have any constants down here, right? So that 1's going to stay there. Yeah? And then what do I have? I've got plus r, right? But down here I'm going to have a minus r, right? So those guys are going to cancel. And then I got a plus r squared, but down here I'm going to have a minus r squared. So those guys are going to cancel. Yeah? And then I've got a, oh no, there's not anything to cancel this r cubed. Good, right? There's an r cubed right there. Yeah, right? So that r cubed plus r cubed is going to cancel that minus r cubed, right? Yeah? Okay, let's keep going. Oh, then I've got an r to the n minus 1 here. Uh-oh, I don't have anything to cancel that down here. Good, good, you own this now, right? What is the term that comes before r to the n? Good. R to the n minus 1, right? So what do I got? This r to the n minus 1 minus r to the n minus 1, they cancel each other. So what's left? There's nothing else left up there, right? And so what do I have? I've got a minus rn to the n. Yeah? Okay, well things are looking a little bit better now. What did I want, right? I want a closed form formula for Sn, right? So what should I do? Solve for Sn. Yeah? Solve for Sn. So how do I solve this for Sn? Well, let's factor out an Sn. Yeah, I heard you guys say that. Factor, right? That's one of our favorite calculus tools. Factor an Sn out of this left-hand side. So when I do that, what will I have left in there? Good. 1 minus r, and that will be equal to 1 minus r to the n. Yes? And so what do I have left? Therefore, solving for Sn, Sn is, divide by 1 minus r, 1 minus r to the n over 1 minus r. You guys all good with that? Yay? Does that make sense? Awesome. Okay. This is a pretty awesome formula, actually, right? Because what does that tell you how to do, right? Let's take a little step back for a sec, right? If I look at this, what is Sn? This is a closed form version of Sn, and this is just summing Sn. So what is this? This is the sum of the first n terms of a geometric series, right? And so that's just a finite thing, right? That's finite. So what does this formula for Sn also allow us to do? Suppose I want to sum the first, I don't know, 3,247 terms, right? What is the sum, right, of n equals 1 to 3,247 of, let's talk about our guy 3/7, right, to the n minus 1. Well, what is the sum of that? Okay, well, that guy, what does this formula say it is, right? What's our r? R is 3/7, right? Okay. Yeah, r is 3/7, and we're going to sum this guy for 3,247 terms, yeah? Well, I could either add the first 3,247 terms, or what could I do? I could use this nice little formula, right? And say that that thing is just the nth partial sum, right? This is S sub 3,247. So what would that be? 1 minus 3/7 to that power, 3,247, divided by 1 minus 3/7. And that is a lot faster, right, than adding up 3,247 terms, right? That's a nice little aside. Okay, so that was an aside though. Now we're going to come back to this piece, okay? So now instead of adding up the first 3,247 terms, we want to add up infinitely many terms, right? Okay. So what do? Well, then we're back right to here. Here's our formula for Sn. What is the sum of this thing? Well, it's the limit then as n goes to infinity of what? We just came up with our nice closed form expression, 1 minus r to the n over 1 minus r. I'm going to erase all of this now to give myself more space. And we just talk about what that limit is. All good? Okay, well, now we're trying to talk about this limit. It's a limit, right, as n goes to infinity. Where's the only n that you see in here? The only n is right here with this term, right? So again, everything else is a constant, 1 and r, right? And so this whole limit simply again depends on, right, the limit as n goes to infinity of r to the n is the key. Again. And what do we know now, right? We're in the case, we already dealt with the case of r outside of 1 or negative 1, right? And we're in the case where we're talking about r being between minus 1 and 1. And what is that limit when r is between negative 1 and 1? 0. Beautiful, right? From our previous work. And therefore, what do we know, right? This limit is going to 0 for, what is another easy way to say r is between negative 1 and 1, right? Without having to use two inequalities. You guys tell me, how do I do it with just one inequality? Absolute value of r is less than 1, right? These two things are the exact same thing, right? Right? R is at most 1 unit from 0, right? R is at most 1 unit from 0, right? Okay, either direction. Okay, so what do I then know? This goes to 0 for, it's easier to say absolute value of r less than 1, right? Absolute value of r less than 1. That guy goes to 0, and therefore what is our limit? That limit is just 1 over 1 minus r. Woohoo! This is the sum of a geometric series. That's kind of awesome. The sum n equals 1 to infinity of r to the n minus 1 is equal to 1 over 1 minus r, right? Whenever the absolute value of r is less than 1. Which means the same thing as minus 1 is less than r is less than 1, right? And it diverges for absolute value of r greater than or equal to 1, right? This is our geometric series result. Let's go back to our two beginning problems, okay? So, back to examples 1 and 2, right, which we really couldn't say anything about. Example 3 was the sum of 2 to the n minus 1. We know 2 is r, it's big in absolute value bigger than or equal to 1, diverges, done. Okay, back to examples 1 and 2. What were they? We had the sum n equals 1 to infinity of 3/7 to the n minus 1. That's what we started with, right? What do we have? It's the exact same form, so we're good. You got to pay attention to that. We'll do an example here in a minute where we don't have that same form. We start counting in n equals 1. We have a number r, right? And we're raised to the n minus 1, okay? So what is this guy, right? Remember, we said that this is just 1 plus 3/7 plus 3/7 squared plus 3/7 cubed, on and on forever. What does this formula say that's equal to? What do we know here? R is 3/7, right? The absolute value of 3/7 is less than 1, so we're golden, right? We have converge, so it's totally fine to say that this is equal to 1 over 1 minus 3/7, right? 1 over 1 minus r. That's awesome, right? But we're not going to leave our answers like this, right? Because we're good at fractions now. So, oops, let me give myself a little more space. So what do we have? 1 over 1 minus 3/7. That's 1 over, what is 1? The same as, right? 7/7, right? I'll do this all out for one time. Yeah? Okay. What is 7/7 minus 3/7? 1 over 4/7. Yeah? What is 1 over 4/7? I should make this. What is 1 over 4/7? Good. 7/4. Yeah? So when I add up all of those guys, I get 7/4. How crazy is that? That's just crazy, right? What about our other example, the sum n equals 1 to infinity of minus 3/7 to the n minus 1? What do we have here? What is r? Negative 3/7. Good. What is the absolute value of negative 3/7? Just 3/7, right? That's less than 1. Okay. Therefore, I have converge, right, by our result for geometric series, right? This is geometric series, right? So what do I know? Not only do I know that this series converges, I know that it converges to what? 1 over 1 minus r, right? What was r? Negative 3/7. So what is minus negative 3/7? Plus 3/7, right? 1 minus r. Yeah? And so what do I have? 1 over, how many sevenths is that? 7/7 plus 3/7 is, good, 10/7. What's 1 over 10/7? Good, 7/10, right? Does that make sense? Okay? This makes sense, right? Because with this guy, we're adding and subtracting stuff. Our final answer is 7/10. Whereas here, we're just adding them all up, right? Everything's positive. Our final answer is 7/4. Which one's bigger? Good, 7/4 is bigger than 7/10. It makes sense, right? It all makes sense. That's pretty awesome. But who would have thought the answers would be that this would add to 7/10, right? That's nutty, okay? And this one, what we started with, adds to 7/4. Another way to write 7/4, right here. What? Anyway. So let's see, what do we want to do now? Does this make sense? Are we good? Do we see it? Yay, we like geometric series. Okay, let's do another example, okay? One of your homework problems. It's always fun to do homework problems, right? And you understand where this whole result came from. It wasn't magic, right? It all just followed the development of what these ideas mean and what we set up to understand in the previous section. Okay. Let's look at another example. So, this is a homework problem. Number 25, section 11.2. Okay. So what do we have? The question is the same. This is converge or diverge. If it converges, find the sum. Now, again, like I told you before, if the question says, if it converges, find the sum, then you pretty much know it's either a telescoping series or a geometric series, right? So this one says n is equal to 1 to infinity, because otherwise find the sum is going to be pretty hard. E to the 2n, whoops, let me just e to the 2n divided by 6 to the n minus 1. All right.
12 p.m.
All right, so I'm gonna try to close this pretty soon. 12 p.m. All right. So what do we need, right? We are looking at this. Looks kind of geometric, but not exactly yet. Okay. So what does geometric look like? Remember, it looks like the sum, right? If we're going to actually use the addition formula, sum n equals 1 to infinity of r to the n minus 1, right? Or, as we said, it's equivalent to the sum n equals 0 to infinity of r to the n, okay? Now, it has to look like one of these two guys in order for, if we have convergence, for it to equal 1 over 1 minus r. Okay, so this one's in the n equals 1 form. So now you could try to get everything in terms of r to the n minus 1, but let's just take a look at what's going on here, okay? We got the sum n equals 1 to infinity. My goal is to try to get a constant to a power, right? I want to separate stuff out. And so this thing is screaming at me saying, how should I rewrite e to the 2n? E to the 2 to the n, right? E squared to the n, right? That's the exact same thing. Rules of exponents. They never leave you, right? And this is, how am I going to rewrite 6 to the n minus 1? Now you might be like, why are you breaking up 6 to the n minus 1? There's already an n minus 1 power there. But let's just talk about some other ways to think about these problems. So that is thinking about rules of exponents. 6 to the n times 6 to the negative 1, right? Rules of exponents. You've got to have your rules of exponents down for what we're about to do for the next several weeks, okay? So let's look at this expression, right? This piece right here is the part that's raised to a power, right, n. So for this one, it's just easier to kind of focus on that because hopefully you're already seeing it. N equals 1 to infinity. Rules of exponents, what is that the same as? E squared divided by 6 to the nth power, right? That's that red part. Then what do I have? Well, times 1 over 6 to the negative 1, right? Now, just for fun, what is 1 over 6 to the negative 1? Good, it's just 6, right? So that's just the sum n equals 1 to infinity of 6, a constant, like the a in the book, times e squared over 6 to the n. Okay, does that make sense? All right, so let's think about this guy right here. This guy, right, is my constant to the n, right? This is an r to the n. And this guy is like my a, okay? Or a constant c, perhaps. You're going to be looking at some results related to multiplying a series by a constant. We'll just call that guy a for now, right? Constant, okay? He's a constant, and this is constant to the n, okay? So what is r for this problem? R is e squared over 6. What can you tell me about e squared over 6? What's your instinct about how big, understanding how big e is? And if you square it, comparing that to 6, bigger or smaller than 6? Good, e squared is bigger than 6, so e squared over 6 is bigger than 1. So if our r here is bigger than 1, do we really have much work to do? What do we know? It's a geometric series, okay? It's a geometric series. Our r is bigger than 1. What do we know? Diverges. Right? Done. Does multiplying a divergent series by a constant have a chance at changing whether it diverges or converges? A constant that's not identically 0. What do you think? Gut instinct? Good. No. Multiplying by 6 has no chance of changing whether it converges or diverges. That's actually one of the homework problems. That's a proof that I just asked you to read in the homework. Okay? So this guy diverges. We're done. Okay? You can, if you want to for yourself, go through the algebra to rewrite this if you would prefer. you could rewrite this and realize that you could also write it as sum n equals 1 to infinity of e squared over 6 to the n minus 1 times e squared, right? And then you kind of have the exact same idea, right? So if you want it to be specifically in that form, but we don't really need it in that form, it diverges, we can't sum it, and so there's not really much more we can do anyway. Yeah? Okay. All right. Now let's do maybe one more problem. You guys up for that, do you think? One more problem, and then we'll call it a day. Yeah? Sound good? Well, we'll call this a video. And it's also one of your web work problems, so that's always good too. Yeah? And we'll look at this little idea where if you have a convergent geometric series, you got to make sure it looks exactly like one of these to use the 1 over 1 minus r formula. Otherwise, you have to adjust for that. So that's what we're going to do right now. So last problem of this. This is web work. This is a web work problem. It's 11.2, number 22. Okay. So what is this one? This one is the sum n equals 1 to infinity of 5 over pi to the n. Okay? So what do we have here? Well, 5 is a constant. The thing that is raised to the n is pi, right? I want to think about these forms, okay? Right now I don't really care so much about where I'm starting to count. I just recognize this is a geometric series. I just want to start rewriting that generating term with algebra. So 5 over pi to the n is the same as 5 times 1 over pi to the n, right? Algebra of fractions. And that is the same as 5 times, now I need a specific r raised to the n, right? Or the n minus 1, right? I've got 1 over pi to the n. So how do I want to rewrite that? I can write that as pi to the negative n, but that's not helpful, right? That's not what we want. Pi to the negative n is not what we want. What do we want? Good. A thing raised to the n. What is the thing being raised to the n here? 1 over pi to the n. Yeah? Make sense? Okay? Okay? So while it's true that that's pi to the negative n, that's not as helpful. Okay? All right. So now what do we recognize? Okay, so here we got a constant, right? Multiplying r to the n. You're going to be doing a proof. Next video, we'll talk about a little bit of help with the proof. One of your homework problems is to prove that this statement is true, that the sum, the series, summing a constant times r to the n is equivalent to pulling the constant out times the series whenever we have a convergent series. So the question is this guy a convergent series? Okay, so what is our r? Our r is 1 over pi. What do you know about 1 over pi, right? Pi is bigger or smaller than 1. Good. So 1 over pi is less than 1, right? And it's positive, right? So if I think about the absolute value of r, right, then we're certainly less than 1. Okay, so this guy converges. Okay. And so once you prove the rule of algebra of series, that the sum of a constant times a geometric series, or a series that converges, is equal to the constant times the convergent series, then this will make sense. We already talked about the divergence case, and so pulling a multiplying constant in or out doesn't change anything, just like all the other rules we've had. Okay, but it's got to be constant. No n's in that guy, right? No n's. All right, so the question now is, what does this guy add to? And that's where we want to end, okay? So let's just think about, instead, let's ignore the 5, and ask, what does the sum n equals 1 to infinity of 1 over pi to the n sum to. And then once we know that, then what? We'll just multiply that guy times 5. So let's finish this out right here. Okay, so now notice, right, this is not in exactly this form, right? It's a r to the n. It starts counting at 1, not at 0, right? And this guy starts counting at 1, but it's an r to the n minus 1. So what do you have to do? Okay, so let's just make sure we understand what this is saying, right? Well, what is this series? This series, when n is 1, it's 1 over pi, right? 1 over pi to the 1 plus 1 over pi quantity squared plus 1 over pi quantity cubed, right? On and on forever. That's what that series is, right? Now, what do we know that these guys sum to? 1 over 1 minus r, right? When r in absolute value is less than 1, right? So, if I had the sum n equals either one, let's just go with 0 to infinity, just to work with that guy for a sec, of 1 over pi to the n. What is that? Well, when n is 0, 1 over pi to the 0 is 1. Plus when n is 1, 1 over pi, plus 1 over pi squared, right? Plus 1 over pi cubed. Yeah? What do I know that sums to? Well, I know that that sums to, because that's that same form, 1 over 1 minus r. What is r? 1 over pi. Right? 1 over 1 minus 1 over pi. Okay? Which we could simplify if we want, right? So that's 1 over pi, so that's pi minus 1 over pi, right? Pi minus 1 over pi, which is pi over pi minus 1, just for a little fraction fun. So that's what that sums to, but what is the guy that we have? The guy that we have, right, just doesn't have that 1, right? This is this part right here is really our series. The sum n equals 1 to infinity of 1 over pi to the n. Yeah? So what does that equal to? Well, solving, right? 1 plus that guy is equal to that. So what is it? It's that minus 1, right? It's everything minus the first term, minus the n equals 0 term. Yeah? Okay? And so if you're starting to count somewhere other than 1 in this way or 0 in this way, if you start counting, say, at 5 and you've got this one, then you got to subtract away the n equals 0, 1, 2, 3, and 4 terms from that guy. Does that make sense? Okay. Alrighty, next time, and there we are. Oh, so we haven't finished this problem yet, right? So what is the sum of this guy? That sum is 5 times that expression, right? Pi over pi minus 1 minus 1. Yeah? Awesome. I think that does it for today, except for the fact that if you wanted to simplify that just for fun, you could find that that is just the same as 5 over pi minus 1, right? Whew. That will do it for this video. So what's coming up next? We'll talk about this idea in general. We'll come up with one more, what we just sort of did here. We'll come up with another formula, and then we'll talk just a little bit about the proof ideas of the algebra of series that allow us to do things like this, which will help us as we move forward into our next sections and start to try to determine convergence and divergence of other series which are not geometric and not telescoping, and so we need new methods whenever the divergence test doesn't kick them out, right? Okay, hopefully this makes sense. And I will see you for Math 236 Home Edition again sometime soon. Bye-bye.